Hello everyone, welcome to this video lecture of 19ScPhyU301. We have been discussing the third chapter, vector analysis, and this is the story so far. When we started with this chapter, we briefly revisited the basic concepts. Then we defined this del operator, which is first order partial differential operator given by dou x into unit vector I plus dou y into unit vector j plus dou z into unit vector k. Then Laplacian operator can be obtained by taking dot product of del operator with itself. Now since it is a dot product, it turns out to be a scalar operator and it is second order differential operator, which is dou 2 by dou x2 plus dou 2 by dou y2 plus dou 2 by dou z2. Now both these operators, del operator and the Laplacian operators, have no values at any given point in space, but when you operate them onto a scalar or vector field, then you can associate value with that operation. When we operate this del operator onto a scalar field, that is called as gradient of that scalar field, which is dou phi by dou x into I plus dou phi by dou y into j plus dou phi by dou z into k. Now you can see that this del is vector operator, whereas this phi is a scalar quantity, and product or multiplication of a vector and scalar is always a vector, which is visible here. When we operate this del operator onto a vector field, gradient of the scalar field gives us a vector which has magnitude and direction equal to maximum rate of change of the scalar quantity per unit length. When we take dot product of gradient of scalar field with a unit vector, then this quantity is called as directional derivative, and that gives us rate of change of the scalar field phi per unit length in that particular direction, which is pointed by the unit vector u. In the previous lecture, we discussed divergence, which is obtained when we take dot product between the vector field and the del operator, which is equal to dou vx by dou x plus dou vy by dou y plus dou vz by dou z. Divergence of vector field gives us flux per unit volume moving out through infinitesimally small volume at the point where we are calculating the divergence. We also saw the divergence theorem, by using which we can convert surface integral to volume integral or vice versa. So if we are calculating this flux of the vector field V over some closed surface, then that is equal to this volume integration del dot V integrated over volume. Now it should be noted that this left hand side is a surface integration and therefore is double integration. Whereas this right hand side is integration over a volume and therefore it is triple integration. In this lecture, we want to discuss curl in detail, which is obtained by this operation del cross V. We will see the concept of line integration over open path and closed path, which then can be connected to curl of the vector field. We will see what is physical significance of curl of the vector field, and then we will consider the Stokes theorem, which is a way to convert line integration to surface integration. Let's begin by defining line integration. Suppose this shaded area is a vector field, and in this vector field we want to calculate this line integration over this path, say from point A to point B. So we are moving from point A to point B in this direction, and we want to calculate the line integration, which is denoted like this. It is V dot dl from point A to point B. This line integration is calculated in the following way. What we do is we first divide this path over which we are calculating the line integration in infinitesimally small segments. So all these small segments are each of magnitude dl, and suppose there are n number of such segments which should be equal to length of the path from A to B divided by length of each of the segment. Now we consider that this limit dl is tending to 0 and therefore n tends to infinity. So in this way we divide the path over which we are calculating the line integration into infinitely many but infinitesimally small segment. Now note that each of this path has the same magnitude but their direction will be different, and therefore if we consider this vector dl at each of the point along the path, though its magnitude is same, its direction is different, and therefore all these vectors dl1, dl2, dl3 up to dln have the same magnitude but their direction is different in general. Then what we do is we consider the vector field at each of the point along the path from point A to point B. These arrows here suggest the vectors at each of the point along the path, and then we consider this dot product V1, which is the vector field at the first point VA, dot dl1, which is line segment at that point, plus then we consider the second dot product v2, which is vector at the second point dotted with dl2 vector, which is the line segment at that point along the given path. And in this way we consider all these n number of dot product and sum them together. Sorry, this is n, and therefore this line integration from A to B is basically this sum of infinitely many dot product. Let me write it like this: I is equal to 1 to n vi dot dli. Now since we have a dot product, naturally this sum is a scalar quantity, and therefore by nature this line integration is a scalar quantity. Now let's consider similar line integration over the closed path. The process is same. This shaded region is the vector field. Suppose we are calculating line integration v dot dl over the closed path. So this is how it is denoted. This circle here denotes that we are considering the line integration over the closed path. Suppose I am considering it in counterclockwise direction in this way. Then what we do is we consider this path, which is now a closed path, and then calculate this sum I is equal to 1 to n vi dot dli. The process is same as calculating the line integration over the open path. The only difference is now we are considering a path which is closing onto itself. So in the similar way, we divide this path into n number of segments along the given direction. Then we consider vector at each of these infinitely many but infinitesimally small line segments, and we consider the dot product at each of these points which are tending to infinity, and then we consider the sum of the dot product over all the paths, and in this way we can calculate the line integration over the closed path. Now obviously this also is a scalar quantity, but in many physical applications it is useful to assign direction to this line integration over the closed path. And how do we do it? We do it by using right hand thumb rule. Suppose we are calculating this line integration, then we can use right hand thumb rule to give direction to this line integration. We hold our right hand such that the four curled fingers except thumb denotes the direction along which this line integration is calculated. So in this case it is counterclockwise direction. You have to hold your hand perpendicular to the screen such that the four fingers are directed in counterclockwise direction, and the thumb then gives the direction to the line integration, which in this case is perpendicular to the screen coming outside. Now note that when we assign direction to line integration in this way over the closed path, the direction of this line integration is always perpendicular to the plane containing that loop over which we are calculating the line integration. Now let's move on to the main topic of this video lecture, which is curl of vector field. Let's define this curl formally once again. For a vector field V, curl is obtained by this operation del cross V, which is equal to this determinant I, J, K. In this second row, we have x, y and z component of the del operator, which are dou by dou x, dou by dou y and dou by dou z. In the last row, we have x, y and z component of this vector, which is vx, vy and vz. And therefore, this del cross v is this vector quantity I into dou vz by dou y minus dou vy by dou z minus j dou vz by dou x minus dou vx by dou z plus k into dou vy by dou x minus dou vx by dou y. So in this way, curl of any vector field is calculated. Let's try to understand the physical significance of curl. For that, suppose this is the vector field. In this vector field, this is the axis, x-axis, y-axis and z-axis. So we are considering the three axes in Cartesian coordinate system, and suppose we have this loop which is oriented in 3 dimension, and suppose we want to calculate this line integration v dot dl for this closed loop along this direction. Now we have just said that this line integration over a closed path can be assigned direction, which can be calculated by using right hand thumb rule. We hold our right hand such that the four fingers except the thumb are rotated along the direction of the path, and then thumb gives us the direction of the line integration. To get the vector which is obtained by taking line integration like this, what we can do is we can consider projection of this loop along all these three planes: xy plane, which is shown here by that gray line, and then consider this line integration for this projection, which will give us the z component. Therefore, z component is obtained when we consider projection of loop in xy plane. Similarly, x component can be obtained when we consider projection of the loop in YZ plane, and Y component is obtained by line integration over the loop, which is obtained by projection of the loop in XZ plane. So in this way, we can consider projection of the loop over each of these plane and obtain corresponding directions for the line integration. Let's calculate one of this component. This blue shaded area represents the vector field. Suppose this is x-axis and this is y-axis, and since we use right hand coordinate system, z-axis is now in the direction perpendicular to the screen, coming outside the screen. So z-axis is coming towards you when you are looking at the screen and is perpendicular to that screen. Now let's consider this loop, which is infinitesimally small and is a rectangular loop where this length is equal to dx, this length is equal to dy, and we now want to calculate the line integration which is along positive z-axis, and therefore the direction over which this line integration is calculated is counterclockwise. Now since this is infinitesimally small loop, we will simply write it as v dot dl over closed loop over closed rectangle. This dot product over the closed rectangle can be obtained by considering this first dot product v1 dot dl1, which is along this line. Let me call that as line 1, plus the second line, which is v2 dot dl2, plus this third line v3 dot dl3 plus v4 dot dl4. So when we consider the sum of the 4 dot product, we will get this integration over the closed loop which is along positive z-axis. Suppose at the center of this loop, vector field v is given by vx I plus vyj plus vz k. Now let's calculate each of this dot product one by one. So this red arrow here in the figure denotes the dot product which is being calculated. We are calculating the first dot product v1 dot dl1. Let's first figure out what is dl1. This is x-axis, this is y-axis, so that z-axis is perpendicular to the screen coming towards you, and therefore we are considering the path which is counterclockwise. Keep that in mind. Now this vector dl1 has magnitude which is equal to dx, and its direction is along positive x-axis, so it is multiplied by unit vector I to make it a vector. Since we are taking dot product v1 dot dl1, it should be immediately clear that we only have to worry about the x component of the vector. What we know is x component of the vector at the center is equal to vx. We want to calculate the x component along this path, along this infinitesimally small vector dl1. Therefore this v1 dot dl1, let me write it like this: v1 x dotted with dx, this is not a vector anymore, where v1x is x component of the vector along this first infinitesimally small line segment dl1. Now what we know is at the center x component of the vector is vx, and we are calculating the x component along this direction at this point. So we have to move along negative y-axis by a distance of dy by 2 to reach that point, and therefore v1x is equal to vx, which is the x component at the center, plus dv1x, where dv1x is the total difference that occurs in the x component of the vector when we move by that distance. Therefore v1x is equal to vx plus dou vx by dou y, rate with which the x component changes when we move along y-axis, into the total change in y-axis. In this case, since we are moving along negative y-axis, it is minus dy by 2, and therefore v1 dot dl1 is equal to vx plus or minus dou vx by dou y into dy by 2 into dx. So in this way we have calculated the first dot product. Now let's calculate v2 dot dl2, the dot product for this line segment. Now dl2 here has the magnitude which is equal to dy. Remember, this is x-axis, this is y-axis, so that the z-axis is perpendicular to the screen coming towards you, and the direction of dl2 is along positive y-axis, and therefore dl2 is dy into j. When we calculate this dot product now, we have to only worry about the y component of the vector, because x and z components won't contribute to the dot product, because dl2 has 0 x and z component. Therefore this is equal to v2 y, which is y component of the vector along this infinitesimally small line segment, into dy. Now what we know is y component of the vector is vy at the center of the rectangle, and therefore v2y can be obtained by considering vy, which is y component at the center, plus dv to y, which is the change that occurs in the y component of the vector when we move along positive x-axis by a length of dx by 2. Therefore dv2y, or y change that occurs in the y component when we change the x-axis, is v dou vy by dou x, rate with which the y component is changing, multiplied by the change in the x-axis, which is dx by 2, and it is positive. Therefore v2 dot dl2 is equal to vy plus dou vy by dou x into dx by 2 into dy. Now let's consider the third dot product, v3 dot dl3, which is along this line of the rectangle. This is x-axis, this is y-axis. dl3 is minus of, because it is now pointed along negative x-axis, minus of dx into unit vector I. Therefore this dot product v3 dot dl3 is equal to v3x, x component of the vector field along this infinitesimally small line segment, into dx, but there is a minus sign now because dl3 is negative. v3x, or x component of the vector field along the given path, is equal to vx, which is the vector field or x component of the vector field at the center, plus rate with which the x component changes, multiplied by the change in the x-axis, which is dy by 2. Therefore v2 dot dl2 is equal to vy plus dou vy by dou x into dy. Now along y-axis into dy by 2, the total change in y-axis or y-coordinate. Therefore, v3 dot dl3 is equal to vx plus dou vx by dou y into dy by 2 into dx, but this is with a negative sign, so let me write it like this. Let's now consider the fourth dot product, v4 dot dl4. dl4 is, this is x and this is y axis, dl4 is minus of dy into j. This dot product now is equal to v4 y, which is y component of the vector field along that particular line, into dy with a negative sign. v4y is equal to vy, which is y component at the center, plus dvy, where dv4y, where dv4y is the total change that occurs in y component when we move from center to this line, which is equal to dou vy by dou x into dx by 2. But since we are moving along negative x-axis, it is minus, and therefore v4 dot dl4 is equal to vy or minus vy plus dou vy by dou x into dx by 2 into dy. Let's now get the z component or this line integration for the closed loop, which is denoted like this: v dot dl over closed rectangle, which is equal to v1 dot dl1 plus v2 dot dl2 plus v3 dot dl3 plus v4 dot dl4. We have calculated each of these dot product in previous 4 slides, so when we add it, what we get is this. This is equal to dou vy by dou x minus dou vx by dou y into dx into dy. I'm leaving it to the viewers to verify this. Therefore, this line integration over the closed loop v dot dl per unit area of the loop is equal to dou vy by dou x minus dou vx by dou y. Note here that area of this rectangle is equal to this length, which is dx, into this length, which is dy, which is dx into dy. In the similar way, we can calculate the x and y components of this line integration over the closed infinitesimally small rectangular loop. Now we won't calculate it in detail. Let's first consider the x component. If we are considering the x component, then this is y-axis and this is z-axis, so that we have a right-handed coordinate system. So the x component of v dot dl for the closed loop per unit area, where this area is area of the rectangle, which is equal to this length is dy and this length is dz. Therefore this is dy into dz. This turns out to be equal to dou vz by dou y minus dou vz, sorry, dou vy by dou z. And for the y component, now since we are considering y component in similar way, we want y-axis, positive y-axis perpendicular to the screen coming outside it, and therefore this is x-axis and this is z-axis, so that when we rotate from positive x to positive y, we get positive z-axis according to right hand thumb rule. This length is dz and this length is dx, which gives us the area of this rectangular loop, which is equal to dx into dz. And now v dot dl over the closed rectangle per unit area of the loop is equal to dou vx by dou z minus dou vz by dou x. Now if you combine all these three components and consider this dot product per unit area for a loop which is oriented in 3 dimension is equal to, its x component is dou vz by dou y minus dou vy by dou z. This is x component minus y component is dou vz by dou x minus dou vx by dou z plus the z component is dou vy by dou x minus dou vx by dou y. This is the z component. Now if you compare this with the definition of the curl of a vector field, it is basically del cross v, curl of the vector field at the given point, and therefore the physical significance of the curl is this: it gives us magnitude and direction of line integration per unit area over the closed loop. Now let's move on to the next important topic of this lecture, Stokes theorem. Suppose this is the vector field as we have done with on the previous slides. In this vector field, this is a finite surface and we want to calculate this quantity del cross v over the surface ts. Note here that this is a surface integration, so it should be a double integration. This surface integration is calculated as follows. What you do is you divide this finite area into infinitely many but infinitesimally small area elements, so that each of this area element, which is shown here, is infinitesimally small. Then you define a vector associated with each of the area element, which is equal to magnitude of the area, which is same for all the area elements, into the unit vector which is perpendicular to the area element at the given point. And while calculating this integration, what you do is you consider this sum del cross v at the given area element. Let's suppose this is the first area element dotted with ds1 plus del cross v at the second point for this second area element, let me write it here, into ds2, and in this way you go on summing over all the dot products such that n is tending to infinity. Now let me consider two terms here, which are del cross del cross v at 1 dot ds1 plus del cross v at 2 into ds2. Now if we focus on to this first term, it is basically the curl for this area element, and then we are multiplying it by the area of this area element, and this gives us a line integration over this closed loop. Suppose it is in this direction, and the second term in the similar way gives line integration over this closed loop, which is enclosing that second area element. Now if you compare this line integration which along the line which is shared by these two area element, what you see is for the first area it is in, suppose, the upward direction as seen on the screen. For the second area element it is in the downward direction now, and therefore they are same but opposite in magnitude, and when you consider this sum, this will cancel out, and what you will get is line integration over this larger area which combines ds1 and ds2. In this way, when you consider this third area element, what will happen is the line integration over this line which is shared by these two area will get cancelled because they will be equal in magnitude and opposite in direction, and therefore you will get line integration over this larger area which combines ds1, ds2 and ds3. And now if you consider this sum over all these n number of dot products, then what will happen is all the terms which are this line integration over lines which is shared by the area elements will get cancelled, and in the end you will get this larger line integration, this finite line integration over a loop which is enclosing that finite area, and this del cross v dot ds, this surface integration, will become the line integration over the closed loop which is v dot dl. Note that this direction is consistent for the curl and for line integration. One more thing, though here we have considered a rectangular loop and therefore all these area element ds1, ds2, ds3 are in the same direction, it is true in general even when we consider a surface which is not a plane, which is a curved surface, this equation will hold true, which is called as the Stokes theorem. And the Stokes theorem gives us a way to convert line integration to surface integration in this way. So this is the mathematical equation which represents the Stokes theorem. This is the last topic that we want to discuss. Let's quickly summarize what we have discussed in this lecture. We first defined line integration. Then we defined line integration over the closed loop and saw how we can assign direction to that. Then we formally defined curl of the vector field. The physical significance of curl of the vector field is that it gives this line integration over closed loop per unit area about that point. So this is what you get when you calculate curl of a vector at any given point. And finally, we considered the Stokes theorem, which is a way to convert line integration to surface integration or vice versa. In mathematical form, it can be written like this. It is del cross v, where v is the vector field. Integration over the surface is equal to line integration over a closed loop v dot dl. We will stop here. In next lecture, we will use Gauss's divergence theorem and the Stokes theorem to write Maxwell's equations. Thank you for watching.